Good morning. Welcome to the second class in this course on RLADP, Reinforcement Learning and Adaptive Dynamic Programming. To begin with, I'm going to constantly be referring to these handouts, which you should have a hard copy of to follow along. In the start of the first lecture, I gave the big picture of where I want to go. And there are 4 steps. First, I want to review the basics of cardinal utility functions, then go to dynamic programming, and with those prerequisites, I'll talk about the core work that's new involving reinforcement learning and adaptive approximate dynamic programming. Most of my time in this course will be on these steps, 3 and 4, but to make sense of these, we have to do this first. Now today, what I'd like to do is first talk a little bit more about this big picture. Talk a little bit more about what is reinforcement learning, give some advanced feeling for dynamic programming and how I'll talk about it, and then I'll start getting back to the prerequisites, more of cardinal utility function. That may look backwards, and a lot of dynamic programming is about how to solve problems backwards from your goal to where you have to start from to get there. So, to begin with, I'd like to talk about what is reinforcement learning. The idea of reinforcement learning is really a pretty simple idea. It's been around for a long, long time. I have a little cartoon right here, which comes from a book that I edited with Miller and Sutton in 1990 from MIT Press. This shows the problem you face if you're a reinforcement learning system. This little man here has a whole lot of choices to make, a whole lot of little levers, U sub 1 through U sub n. He has some information, a bunch of lights, x1 through xm, that shine off and on. And then he has this big thermometer, which is really a measure of how well he's doing. What he wants to do is to move the levers somehow to get the highest possible score on his thermometer, on this utility function, U. He doesn't know what the relations are between the levers, the information in the lights, and the thermostat. He has to learn. That's a learning problem. So that's basically it. There's some things about notation that are very important as we get mathematical here. Under the levers, I have written labels, U sub 1 through U sub n. Each lever corresponds to a control variable, something the little man decides. What does he want U sub 1 to equal? What does he want this number to equal? He chooses all of these numbers. Together these n numbers form a vector. Okay, it's called a control vector, little u. And that's standard notation in control theory. The lights I've indicated with x sub 1 through x sub m, and each of those is described by a number. This isn't exactly standard notation. It varies a little from field to field how they indicate what you sense in the environment. And of course the utility function is standard. In this example, the guy has n numbers to pick. N numbers to pick, that really forms a vector. So the set of n numbers is a control vector. We usually indicate it as a little u with an underline. And likewise, this is a sensor input vector indicated by x. There are some dynamic programming problems which are more complicated and some which are simpler. In this example, you have n real numbers to pick. But there's some decision problems where you just decide to go to the left or the right. Bang, bang, control. Simple binary choice. There are other problems that are more complicated. Like you're trying to set the voltage at every node in a complex graph representing an electric utility. So problems in RLADP can be choosing from 5 alternatives, can be choosing a vector, or can be choosing a field across a graph, something like that. There are these different levels of simplicity, and my examples today will be of the simplest kind, but in time I'll get through those different levels of complexity. This is one more chart on what is reinforcement learning. It's basically the same thing with the notation, and we need to know the notation. This is actually a little more general than what I showed before. Here I'm using big X to denote the whole collection of inputs. I didn't do an underline. This might be a vector, it might be a discrete choice, I'm showing the general case here. We have sensor inputs. The reinforcement learning system has to decide on its actions at each time t, and at each time t it gets a reinforcement signal. In psychology, people call this a reward signal. But I need to warn you, the literature on ADP and reinforcement learning is very complicated. Some of the papers in psychology don't work very well when you try to use it as engineering. Even though they say they do, a lot of times they don't. So I use the notation that you'll tend to find in the papers that tell you how to make things that work. But it's also important to know how to read some of the other papers. So in psychology you'll see a little R sometimes, but capital U says this person knows what a cardinal utility function is. And if they don't know that, they really can't understand dynamic programming. The world we're trying to influence, in control theory they call it the plant. In animal psychology they talk about the environment the animal is living in. There are a lot of different names for that external reality. So this is the basic idea of reinforcement learning. Now I can say briefly, the difference with dynamic programming is that in dynamic programming we actually have some idea what it is we're trying to maximize. And it's usually important to use that information. And even brains have some built-in knowledge of what it is they're trying to do. So adaptive dynamic programming is really the general case, but reinforcement learning is a nice, very important special case of this larger realm of approximate dynamic programming. There are also some old reinforcement learning methods which don't really maximize utility. Those are sometimes called reinforcement learning too, but that's not what I'm going to be talking about. So now let me go back to the big picture in more detail. There are, again, 3 basic steps that I want to talk about in this course. I want to explain more about cardinal utility and Bayesian probability. We really need to know what utility functions are very well before we start using them in practical problems. And in this lecture I'm going to start getting into a subject called decision analysis, risk management. For those of you who want to solve engineering problems and don't care about money, I have to apologize, you may be bored. But even in the real world, engineers sometimes need to know something about money and economics. That sometimes turns out to be more and more important the further you get into real world engineering. So I'm going to talk more about economics and money and risk analysis in this lecture and the one immediately following it, in order to establish more. What is a utility function? What is a probability? What do these things really mean? What are we trying to do? Then I'm going to talk about dynamic programming. And this is really the core of the course. Dynamic programming really came from Richard Bellman, who actually was a friend of John von Neumann. I mentioned that John von Neumann invented the cardinal utility function, and as soon as he did, the question arose, how do I maximize this in an uncertain world over time, when there are stages and stages of decision over time? I've even heard Richard Bellman's daughter, Christy Bellman, talk about how John von Neumann used to bounce her on his knee as they came and talked about all this stuff. So dynamic programming is really 2 things. It is a method to calculate optimal decisions based on the Bellman equation. But it's also the Bellman equation. So one thing you really have to know very well to do work in this field, you really have to understand the Bellman equation very well. Bellman equation is to decision, control, and brains what Maxwell's laws are to electronics and photonics. It's really fundamental. I have seen some papers on control theory or physics where people have 200 equations and they don't really understand any of them, and they get into real trouble. For applications in this area that are useful, it is critical to have a really deep understanding of the Bellman equation. And the reason I'm going to talk about utilities a lot is to make sure you have the prerequisites to really understand this equation. I should mention, however, in ADP we don't only use the Bellman equation, and we don't only use forms of it. We also use the gradient of the Bellman equation, which is also extremely important. I'll talk a little bit more about that. Everything I talk about, I'm going to talk about time t plus 1. Some people call this sampled or digital time. And there are other people who work with continuous time, but discrete time is a little easier, And anything you want to do, you can do pretty much in discrete time anyway. So in this course, I'm going to focus on discrete time, one decision, then the next time period, then the next time period. So let me give an example of the Bellman equation so that you understand what it is I want you to understand as we get into utility functions. Suppose we have a problem where x of t is the state of the world at time t, u of t is our action or decision at time t, and supposing it's a problem where the probability of different values of x in the next time period depends only on the present state x of t and u of t. Okay? In other words, when we take different actions, we get to different states in the next time period. If the probability of getting to any given state in the next time period is just a function of what we see, x of t, what we see and what we do, then that's a Markov decision problem. And by the way, the utility also should only depend on what we see and what we do. If this decision problem meets that, it's called a Markov decision problem. Some people call it a fully observed system. What happens is a function only of what we see and what we do, and we don't need other information except what the function is. In case of a Markov decision process, the Bellman equation specifies exactly what the optimal strategy of action is in an uncertain world. I'm showing two versions of the Bellman equation here. One is just a simplified schematic version that I use in a lot of introductory slides on brains and optimization. And the other is a more detailed version, which is really exactly true. It is an exact Bellman's equation. The simple form shows really three terms. U is your utility function. There's a little thing called gamma, which people call a discount factor in artificial intelligence these days. And then there's J, which is another measure of value that I'm going to talk about a whole lot in this class. Okay? And the idea is your happiness, your strategic value at time t, is the sum of your utility and where you expect to be tomorrow, discounted by something like an interest rate. The more full version of the Bellman equation, which I hope you're going to understand in much more detail as I get into it, is this equation here. I'm going to go over many times. It has a thing called J star. This represents the best future utility you can get if you take the optimal policy. And the equation says that the best value of this is the maximum over possible actions little u of the expected value of the sum of two terms. This is your immediate utility or satisfaction. This is the strategic value of where you are in the future, discounted by an interest rate R. And this is how economists do it, and this is really the right way to look at this. If you don't care about the future as much as you do about the present, in your value system, you have an interest rate. And it's possible to do a Bellman equation with an interest rate. Of course, you can set R equals 0, in which case you care about the future as much as you do about the present. But dynamic programming gives you a choice. You choose what your interest rate is. You choose how much you care about the future. Now, there's a simple relation between these. Gamma is just 1 over 1 plus R. And for numerical work, this is often more convenient. But to understand what you're doing, it's really important to know about interest rates. That's a critical part of defining what your values are. You'll notice I use these angle brackets to indicate expectation value. The expected value of an uncertain variable. I'll talk a little bit more about expectation values. This notation comes from physics. I find it's a little more convenient than the big E that they sometimes use in psychology. So in this equation, the brackets are expectation value, R is an interest rate, gamma is just 1 over 1 plus R, and in this equation I'm going to be using the same notation I use in Chapter 1 of the new book on RLADP by Lewis and Liu. There are many different notations that different people use. I'm going to have to talk about a lot of different fields, so I will start showing you their notation. But this is the preferred notation. If at the end of this course you really understand everything in Chapter 1 of that book, I'll be very happy. But it's not simple stuff, and they're prerequisites. And of course, the big part of the course will be about RLADP and its connection to the real world and so on. So now, I promised I would explain a little bit more about what is a utility function, and talk a little bit more about risk analysis. In this beginning part of the course, I'm going to be talking a lot about the work of Howard Rafa, I mentioned before. Howard Rafa from the Harvard Business School was another important historical figure in the development of this field. Just like von Neumann and Bellman, Rafa translated the core ideas of von Neumann and a bit of Bellman into practical tools that people can use in managing business, in managing stock portfolios, in making decisions about oil drilling. A lot of people use Rafa's decision analysis today. On the previous handout, I showed a reference to the book by Rafa. There is a book by Rafa called Decision Analysis. Came out in '68 and reprinted in '97. There's some popular books that may cover the same ground, I don't really know. But there are also some Wikipedia articles. Especially good at Wikipedia, there's an article called Decision Tree. And then there's one on Bayesian probability, which helps a little bit. And I'm actually going to refer to the Wikipedia article because I know any of you folks can get it pretty easily. So when Rafa translated utility functions and dynamic programming into simple terms that people could use in business, he showed people how to do things called decision trees. And this is an example of a decision tree. This is a decision tree that represents von Neumann's example about hamburger and steak, which I mentioned last time. This is the same example, except I'm going to be a little more formal about how I present it. In this example, I'm going to pretend that you have already decided that a hamburger is worth about half as much. It's halfway between a steak and no food. Just for this example, I could put in a different number. But just to show how things work, it helps to use numbers, arithmetic numbers, instead of too many variables. In this decision tree, you start out with a choice. This is the choice von Neumann asks you about. He asks, do you want a hamburger for certain, or do you want to have a 50-50 chance or an uncertain chance between a steak and no food at all? Okay? So you start with a choice. If you pick hamburger, the probability is 1. You know the outcome of hamburger. You get to this outcome, 50. If you pick the coin toss, there's a probability P that you'll get steak, which is worth 100 to you. There's a probability of 1 minus P that you'll get no food at all. Okay? So this is just a simple decision tree showing the same thing. In decision trees, there are always 3 kinds of nodes. Howard Rafa spent a lot of effort trying to give examples to people in the business world how to take a complex decision problem and express it as a decision tree made up of choices and chance nodes, where you don't know the outcome of the choice, but you can guess the probabilities. And then at the end of the process, there are outcomes. Outcomes are shown in triangles. Uncertain events, chance nodes, are circle. Choices are squares. And this is just like what you'll see in the Wikipedia article. I have put labels on each of these nodes just so that I can talk about them. You put in your primary utility at the end. You have to decide what is your evaluation of the outcomes. You can't decide what the right decision is unless you make up your mind what outcomes you want and what outcomes you don't want, and what outcomes are in between and how far in between they are. You have to decide how you evaluate the outcomes before you can make a rational decision. And the way you calculate the best decision, there's a thing called working back through the tree. This is like it is dynamic programming. It's a special case where you work your way backwards from the final result to the initial choice. So here, if your utility function here is 0, and in this outcome it's 100, you can ask, what is the value of being in this node? if you pick this node, how good is it? Well, how good it is the expected value of utility. And what is the expected value of utility when you're here? Well, expected value, it's very important to really know this equation. What is expected value? The expected value is the probability of this outcome times its utility, plus the probability of this outcome times its utility. The sum of those two is the expected value. And in this case, it's easy to work out. The utility of being here is p times 100, because this one is 0. So the expected value works out to be 100 times p, whatever p is. And if we don't know what p is, we don't know how good it is. If you don't know how good your chances are of getting a steak, you don't know how good this coin toss is. On the other hand, with a hamburger, you know for sure. This is not your utility function, because this is not your ultimate value. This is an intermediate measure of value. We call it J star. It's the same thing that's in the Bellman equation. And then when you make a choice, you look at these two values. Which is bigger, 50 or 100 times p? Well, if your chance of a steak is more than 50%, you'll go with this, because 100 times p is bigger. But if your chance of getting a steak is less than 0.5, then this is a bigger number, and you'll choose the hamburger. So that's the basic idea here. There are a few important lessons you can get. Next week I'm going to talk about a more complicated example. But just studying this example is worth a lot, because there's some important ideas here. The most important ideas, there are 3 important ideas here. The first critical idea is you really have to figure out what your utility function is, how you evaluate the different outcomes before you can make a rational decision. Howard Rafa has lots and lots of case studies about how a decision analyst can talk to a business leader to try to find out, what does the business leader really want? How important is it not to bet the company on a high-risk alternative? How much can he afford to lose? How much does he want for upside potential? There are a lot of stochastic things where a decision analyst can talk to a business leader to find out what he really wants. What is his real utility function? And you can run the problem different ways with different utility functions if you're not sure what the guy is telling you. So there's a whole lot of work in Rafa's book about how to figure out what your utilities really are. The second thing is, when you look at a simple example like this, you can say, wait a minute, sometimes I'm really hungry and I would take the hamburger because I want food for sure. But sometimes I'm not so hungry and it wouldn't be worth anything unless it was really good, like a steak. And your utility for this problem can change. And the reason is that your personal utility function in life is a lot more complicated than these 3 states. In practice, whenever you solve a real-world decision problem, what you're doing is focusing on a narrow domain where you can simplify things, and you have to make up your mind what you want now in this domain. It's not your total utility function, it's something simplified and approximate. And all of life is full of these kind of approximations. In fact, sometimes it's really a case of optimization within optimization. In one narrow domain, you're trying to get money for your next project. In a larger domain, that next project may be what you're trying to do. And then in a larger domain still, maybe that project is supposed to serve some higher philosophical value, which is your real utility function. So in practice, we have chains and chains of approximation. But whenever we use decision analysis, we have to figure out, how do we value the outcomes we're looking at here and now in this problem? The third important thing you can notice if you think about this, what if you don't know what P is? What if you talked to some restaurant owner and said, well, I might give you a steak, I might give you nothing? And you have to try to guess what that probability is. In the real world, in business, you want to know, what is the probability people are going to want this product? You can't go to some handbook of physics and find the probability there. In the real world, we always have to make decisions. Our brains are designed to make decisions. And in order to make decisions, we have to estimate probabilities as best we can. In a technical sense, whenever we do probabilities here, these are actually conditional probabilities. They are probabilities conditional upon the best knowledge we have. which is basically subjective. It's the knowledge we individually have, and if we can get scientific numbers, that's good, but we just got to do the best we can, and sometimes we have to change our opinions as the probabilities change. We have to be ready for that. But estimating subjective probabilities is the core of being rational. And Rafa talks a whole lot about subjective probabilities. There's an article called Bayesian Probability in Wikipedia. Talks a little bit about this. I don't think they really get to the heart of the matter. Because since life is making decisions, conditional probabilities really are the fundamental ones for us. And everything else is basically a tool for figuring out the probabilities we need to make real decisions. So, as I say, next week I'll talk about a more complicated decision problem, and we'll get deeper into what is a utility function, what is a probability, and how do we make rational decisions working back from where we really want to go.